All right, let's have a quick comparison video between shells and washers. Here we have a region defined by y equals 2x and y equals 2, rotated around the vertical axis x equals 3. Let's use the shell method and let's use the washer method. Shell method around a vertical axis will be in terms of x, and a washer method around a vertical axis will be in terms of y. Let's look at our shells. So shells, our heights are always within the region, and they're always the vertical distance between the top graph y equals 2x and the bottom graph y equals 2. Since we are integrating by x, let's start our volume. Volume will be the x bounds. The x bounds in your region go from 1 to 2. So from 1 to 2, we're going to integrate on the surface area of a particular cylinder, and that's going to be 2 pi radius times the height. Radius, let's do this, radius times the height, dx. So 1 to 2, 2 pi, we'll need our radius and our height. We drew our height in the picture. It's going to be the vertical distance. Again, our radius in the picture goes from that height always out to the axis of rotation. And that radius distance, we need to account for this piece over here. This piece is a distance x, because it's the horizontal distance from the y-axis out to the curve, and the curve is x equals y over 2. So we're either going to represent this distance here as x or y over 2, but we're going to use x because we're integrating with respect to x. So our radius is going to be 3 minus x equals 3 minus that x3, because the distance from the y-axis out to the axis of rotation is 3 minus x. So we have 3 minus x for the radius. The height was the top curve minus the bottom curve, 2x over 2x minus 2 dx. The washers. Washers by y, we would have 2 radii. Again, the distance from inner radius goes from the axis of rotation out to the first curve. There's our inner radius. Our outer radius goes from the axis of rotation out to the further curve. And that's our big R. And we already have an idea how big the big R is. This distance is x, but we're going to write it as y over 2. Again, the horizontal distance from y-axis out to the curve is x equals y over 2. So our radius is going to be 3 minus y over 2. 3 minus y over 2 for the big R. Little r is looks like it's 1 all the time. So our volume for washers, we're integrating by y. The y bounds go from y equals 2 to y equals 4. 2 to 4 pi big R squared minus pi little r squared dy. So we have definite integral 2 to 4 pi big R squared minus pi little r squared dy. The little r was 1. The big R was 3 minus y over 2. 3 minus y over 2. Let's see. I want to encourage you to try this again on your own and put the vertical axis to the left of the region, and put the vertical axis, put the vertical axis between the y-axis and the region and see how that works out. Put the vertical axis over here to the left of the y-axis, see how that works out. Let's keep going. Same region that we just dealt with, except our axis of rotation is down here. It's horizontal and it's above the x-axis. Okay, so if we're rotating around a horizontal, shells will be in terms of y and it'll be more difficult. Washers will be by x and typically easier. All right, shells by y, height within the region, and it's parallel to the axis of rotation. Radius for that height is here. That'll be a little trickier. So let's start our volume. We're integrating by y. Our y bounds again are 2 to 4. 2 pi, we're going to need our radius, and our radius, let's see, we're integrating by y, and this distance down here is 1. That's 1. And our, let's see, the distance from here down to the y-axis, this is the vertical distance out to this point on the curve. The curve was y equals 2x. And again, we're integrating by y. So this vertical distance is either 2x or it's y, and we're going to write it as y. So our orange r distance for the shell, distance from axis of rotation out to the height, is going to be y minus 1. So our big R there is going to be y minus 1, and our shell height is the right curve minus the left curve. That's going to be 2 minus, it's even trickier, let's see, this distance for the height. That is y over 2, we already know. So our height is going to be 2 minus, 2, because we go from the axis of rotation out to there. That's going to be 2 minus y over 2. 2 minus y over 2 dy. Washers, we have an inner radius here, and we have an outer radius from the axis of rotation. Okay, so we went from axis of rotation to the lower curve, axis of rotation out to the upper curve. That's our big R. So volume by x, we're integrating by x, and the radii go from the x bounds 1 to 2, 1 to 2. Pi big R squared is from the y-axis, y equals 1 out to the curve. And let's see, okay, so we need this distance down here. This is 1. And our radius is part of, let's see, the axis of, the x-axis out to the curve, and that's a height of y equals 2x. So that's 2x. So our radius is going to be 2x minus 1 for our big R, 2x minus 1, and squared, pi big R squared minus pi little r squared dx. And the little r is, looks like it's a height of 1 all the time, because it goes from y equals 1 axis of rotation out to the curve. So that's 1. There we go. Let's keep going. New region. I didn't shade it in this time, but it's this region between y equals root x and y equals x squared. If you rotate around a and back to this one, I want to encourage you to use another horizontal axis of rotation and put it down below the x-axis and see how that would work. Put it above the region and see how that would work. Shells, let's see, we're rotating around a horizontal thing. So shells will be by y, washers will be by x, and let's do that. So volume equals shells by y. The y bounds go from y equals 0 to y equals 1, 0 to 1. The washer bounds for by x also go from 0 to 1, 0 to 1, except these values are x values and these values are y values. So shells would be 2 pi. We need a radius and a height. Our height is distance from left to right within the region. There's our height parallel to axis of rotation, and our radius goes from the axis of rotation out to that height. Could draw it there. We could draw it over here. It wouldn't matter. Let's see. Let's put it back. Back there. So, yeah. Okay. So our radius is going to be, that's our radius, and yeah, that radius is going to be 3/2 minus whatever this distance is down there. And that distance is the vertical distance from the x-axis out to that curve. And that curve is let's see, y equals root x. If we solve for x, x equals y squared. So our radius is 3/2 minus the curve height, y squared. The height is right curve minus left curve. Right curve is x equals root y. So we have root y minus this curve, and that curve is y squared dy. And I'm just thinking this should also work the same if, let's see, the height stays the same. It's root y minus y squared. But the radius, I'm thinking about that radius, to go from 3/2 to there. I'm going to pause a second and think about that. I'll be right back. Okay. I thought about that some more, and I made a mistake in our integral there. So our radius, it does go, here's the x-axis at y equals 0. Here's the y equals 3/2 axis of rotation. We want this distance. And so that distance is part of 3/2, and we got to subtract off this distance. And I wrote that distance as y squared, and that's not true. Y squared would be the horizontal distance from the y-axis out to the curve. That vertical distance is right here, is the distance y. Whether we're considering this radius going to this curve, or the radius going to this point, or the radius going from here down to the blue curve, that vertical height we're subtracting off is always y. So I'm going to go back to our take off the square. Now it works just fine. For washers. Okay, so we're rotating about this axis. We need an inner radius that goes from the axis of rotation out to the first curve. We need a larger radius axis of rotation out to the bigger curve or the further curve, and in both cases we're going to subtract off these remaining distances. For the red curve, this remaining distance is a height y, and that y is root x, so that's root x. And for the big R, we're going to subtract off that remaining distance. That is also height y, but it refers to the blue graph. That distance is x squared. So we'd have pi big R squared. The big R is 3/2 minus x squared, and we're going to square that, minus pi little r squared dx, and the little r is 3/2 minus root x. And then the last one, let's think. Okay, so we're rotating vertical. Shells will be by x, washers will be by y, and shells volume by x. The x bounds are 0 to 1. Washers x bounds 0 to 1. And we need pi big R squared minus pi little r squared dy. We need 2 pi radius times height dx. All right, so height over here, vertical distance within your region by x, that's going to be top graph minus bottom graph. That's going to be root x minus x squared. Root x minus x squared. Then the radius is the axis of rotation out to that height. And whether I drew okay, so this distance is always 1/2. And this distance is always x, whether I draw the radius where I did, whether I draw it there or down here or down here. The radius always goes from the axis of rotation out to the height. So all these radii are the same, and they're always 1/2 plus x, 1/2 plus x. Then lastly, for the washers, an inner radius out to the curve, first curve for this left curve, and then a bigger radius. In both cases, this is 1/2. This distance is 1/2 from axis of rotation to the y-axis, and then you have these other distances. In the little r case, this is a horizontal x distance, but it goes to the red curve, and that red curve is represented as x equals y squared. So this part is y squared. For the purple part, it's x equals root y. All right, so our big radius is going to be root y plus 1/2, 1/2 plus root y. Our little radius is going to be 1/2 plus y squared. Y squared. Okay, that'll do it. Y'all take care. Reach out if you need to. Again, I want to encourage you to try work through these problems. Also, try the regions again with just different axes of rotation, and see how you do. Okay, bye. Have a good Saturday. Good weekend.